All right, so continuing with 22.3, looking at the graphs, we're going to describe the values of A and B. Let's kind of do the check your understanding just to kind of refresh some information from yesterday. I'm feeling that we probably need that. So describe the values of A and B for which the exponential function a to the bx is always positive. So it's asking for when it's always positive. So if you refer back to the graphs that we did yesterday, the A, B, C, and D, if it's positive, is it above or below the x-axis? Above. So where is this? Where is it always positive? When is it above the x-axis? Yeah, when the output's positive, so above the x-axis when it's in the positive y values. So I'm not asking if it's increasing or decreasing, but in order for this function to always be positive, in order for a to the bx to always be positive, what has to be true about our a and b values? They both have to be positive, right? Regardless if b, whether it's growth or decay, whether b is greater than 1 for growth or between 0 and 1 for decay, a and b have to both be positive in order for this to be a positive function. Describe the values of a and b for which the exponential function a to the bx is increasing. So now we want it to be increasing, and we read a graph from left to right. So in order for it to be increasing, we need to, our y values need to be growing. Why is not working? All right, so is this, nope. All right, so an increasing function looks like that. So from left to the right, it's increasing. So that would be a increasing function. How else could increasing? Is that the only way? No, if it was linear, we'd have it would be the positive slope. So that is this increasing? Yes. So what has to be true about a and b if we're looking for an increasing function? Y has to go up. So if we're looking at a and b, looking back at your A, B, C, D graphs that you sketched yesterday, which ones have increasing? What has to be true about A? What has to be true about B? Right, they have to be positive, but are all situations where A and B are positive, are they all increasing? No. Which one is decreasing? Is D. What about the equation? If I had y equals 2 times 1/3 to the x, is that an increasing function? If we pull that up on Desmos, is that going to be increasing? No. So what has to be true in addition to, so being positive isn't necessarily enough. What else has to be true? Right, so what do we have for our, can I write them? No. Well, you have to use your finger.
I'll do the second.
Sure. And you can't erase. So.
Oh, I can't.
Oh. Okay. Wait, what did I say? Oh, that's oh. Can you not use the marker?
We can't erase.
You can't erase.
Why was all the broken?
It's not functioning correctly. So you gotta push hard.
I don't remember my name.
I'll do that.
Can the first one? It's 0.
Perfect.
Alright, so everyone's tables look like this. So we're just substituting our x terms into the equation. So then we have our graph here. So Grace, you're going to graph both of those together.
Is the number at the top
X.
okay. I mean, like this. Oh, I can't figure out. Shit,
Draw harder. You won't.
exactly. Great. Wow. Oh shit.
Is that what it looks like?
Yes, that's our f of x. Now what about the g of x?
Where's the not?
It's there. You do it.
Oh, it's on there, so then it finds it. It's like this. Something.
Okay, so it's similar, but what's different? So so it says examine the graphs of f of x and g of x. Compare the values of each function from x equals -2 through x equals 2. So if we're looking at -2, which wasn't up here, the linear one. Here, I'm gonna. So we had at 1, 2. So here's 0 at 1. So is yours similar to that for the f of x? Right?
Yes.
And then for the g of x,
Is it parallel?
not parallel. Oh wait. Can't erase, no matter how many times. It's the units are it's going by half units, which is kind of confusing. So 1 is negative.
Yep.
Again.
One is not the right.
Yeah, it's supposed to be here. So between the board being off and then me failing epically. So there, and then 2, 4. So that's our f of x. And then our g of x. 1, 2, 3, 4. And then after that it changes. So just kind of taking Grace's graphs and extending them into the negatives. Which function is greater on this interval? So if we're looking at from -2 to +2, which one is greater on that interval? So at -2, which has a higher value, the g of x or the f of x? Which one has a greater value, the g of x or the f of x? The -2. G of x, right? Because it's positive, and then the f of x is negative at that spot. And then, but if we look at +2, they're both equal, right? They're both equal to 4. And then even at 1, they're both equal to 2. So they have some common areas, but in general, that g of x has greater y values than the f of x. All right, so examine the values of f of x and g of x for x is greater than 2. Which function is greater on this interval? So if this was a candy function, which function is going to give you the most candy after when x is greater than 2? The g of x, right? Because it's getting bigger. We had g of x, g of 3 was 8, and f of 3 was 6. 8 candies are better than 6 candies. And then they just keep getting further and further apart as we move forward. Do you think this will continue to be true as x continues to increase? Explain your reasoning. So do you think there's going to be ever a point when our f of x function takes over and passes the g of x function after 2? Which is this? Which function is greater on the interval when x is greater than 2? We did do 9, and then we did 10a. So looking at this, so if when x is greater than 2, which equation is going to produce more? The g one, right? So and if we look at our table, our g function for g of 2, they were equal, right? They were both 4, but g of 3 was greater than f of 3, right? And g of 4 is greater than f of 4. And g of 5 is greater than f of 5. So so we said that the g function was greater. So then looking at 10b, will this function to be true, or will something happen when the f function, like all of a sudden takes over the g function, becomes greater output? And if I go to Desmos and graph them, so we had y equals 2x and y equals 2 to the x. So looking at this, do you think those lines will ever cross again? No, I can keep zooming out. But I mean, by the time I input a value over here, what's going to happen? So if I would do y equals 2 to the 100, I get this number over here. So 1.27 times 10 to the 30. Well, that's bigger than 200, right? If we're looking at candies, do you want 200 candies or 1.26 times 10 to the 30 candies? Right. We want as many candies as possible. All right, so will they ever, they touch at x equals 1 and x equals 2, but will they ever touch again?
No.
All right, so looking at number 12, does the graph that we just did in Desmos, does that support our prediction from 10b? Will they ever intersect again? No. Which graph increases faster, f of x or g of x? So looking at Desmos, which one increases faster? G of x or f of x?
G.
No.
G, this one's increasing, the blue one is increasing faster, right? It's getting higher y values much quicker. And you can see, look at, for 200, our f of x, we have to go all the way out to 100 to get there. But for the blue line, we're at 200 at, fingers too fat, what's it say? Oh, you're so smart. All right, so 7.644. And so, do you want to, go out to wait 100 to get 200 or 7.6? 7.6. All right, so the exponential function is getting bigger faster. Alex believes that for the linear function f of x equals 50x and the exponential function g of x equals 2 to the x, the value of f of x is always greater than the value of g of x. Glenda believes that for a linear function f of x to always be greater than an exponential function g of x, the graph of f of x must be very steep, while the graph of g of x must be very flat. She proposes graphing f of x equals 50x and g of x equals 1.1 to the x to test her conjecture. Test Alex's conjecture by graphing f of x equals 50x and g of x equals 2 to the x on your graphing calculator. Do you agree or disagree with Alex's conjecture? Explain your reasoning. All right, so let's graph them. We already have 2 to the x graphed. So we're going to change this to 50. So is Alex correct? Is f of x always greater than 2 to the x? So our 50 to the x, 50 times x is our red line, and our blue line is y equals 2 to the x. So is the red line always above? Is it always at a greater y value than the blue line? And we can zoom in. So here, looking at this, our red line is greater than our blue line, right? So this has a higher y value than this one. So here we're at, whatever this line is. And so here, like at 6, we have, almost 300, and then we're at the same amount, but we have to go to the right to 8. So it has a higher, to get the same output, it's a higher input. But if I scroll down, go up, what's happening to my lines? What's happening? They're getting closer, right? And then what's happening right here? They're intersecting, and they have an intersection point at 8.778. And so at that point, they have the same output. But then after that point, what's happening to our red line? Is it more or less than the blue line? It's less, right? So it's underneath. And so for the same output, we have to go further right. We have to put in a higher number into our f of x equation, into the 50 times x. So, is Alex correct? Is his conjecture a good one? No, we just disproved it. F of x is not always greater than 2 to the x. All right, so now we need to look at Glenda and look at her reasoning. So she wants to test f of x and then 1.1 to the x. All right, so here's Glenda's. She said that if our base is real small, if it's a real slow growth, so like 1.1 to the x, that maybe that is always less than the linear function 50 times x. Is hers a true or false statement? Is 50 times x always greater than 1.1 to the x? No. It's just they're crossing way out here, right? We have an intersection, so they don't. 50 times x is greater until we get to 88. And then what happens after that point? Now our exponential function is greater. And what this is an example of why you shouldn't put your money in a mattress or in a closet. That you should, put it into a bank account, even if it's earning a small amount of interest. Some interest is better than no interest. And so even a small amount of growth is better than no growth. All right, so we did that. So should Alex revise his conjecture? Yes, because at some point the 50, even though 50 is a very steep slope, it's not always bigger than 2 to the x. And then what about Glenda? Should she revise her conjecture? Is 50 times x always going to be bigger than even small growth? Nope. At some point, small growth will even overtake 50 times x. So is an exponential function always greater than a linear function? At some point, an exponential function is going to be greater than your linear function, right? At some point. It may, it depends on your window. If you're looking at a small window, like with Glenda's, we had to go all the way up to 88. So if we were looking at a situation in here, then the exponential function is less than the linear function. But at some point, it's going to cross. I mean, even if I change the exponential function to 1.01, at some point, it's going to be greater than 50 times x. It'll just be further out. All right, do you guys have questions? All right, so then you may get started on your homework. Your homework is going to be 21 to 23.